Hello, everyone, and today we have a last part of our introduction to concurrent programming mini-series by our fellow speaker, Nikita Koval. And this part will be devoted to relaxed data structures for parallel organisms, whatever it means. So, welcome, Nikita.
Oh, hello, everybody. And yeah, this is the third talk for this today. So the second talk today.
Yeah.
So
Okay. What do you mean by relaxed data structures? Are we sleepy or lazy or something like this?
That's a great question. I would explain you this way. So let's look to the slides. And the previous two talks, we covered the state-of-the-art tribal stack and Markov-Scott queue algorithm. Then we discussed the modern featured-based queue, as well as the flat combining technique to make any sequential algorithm concurrent and efficient. And all these algorithms, all these techniques helped us to build solutions that are linearizable, right? So we expect the same behavior as in the sequential implementation. And when we talk about relaxed data structures, it means that we sometimes probably we don't really need to strict semantics. So we don't really need linearizability sometimes. Let's imagine the following situation. For example, you have a queue. And this is a queue for tasks. And you have a lot of consumers that process the tasks. And by default, your queue is linearizable, right? So it guarantees you strict FIFO. But in practice, it's totally fine if your queue is not linearizable. If it's not FIFO, it's fine if it's close to the standard FIFO queue, but with some delta behavior. So if you extract an element that out of order, but do it quite rare and don't really affect the fairness of the tasks processing, then okay, no problem. And if it helps you to improve the performance of your overall system, then it would be a great solution, isn't it? That's what
okay, maybe.
Okay.
I think before we dive in the deep details and follow the presentation, I would remind our listeners that we encourage you to ask questions in our chat, and we will also be glad to see your ranking of this and our previous presentations. So we would know, do you like it or not, and how it could be improved. So, and in the end, we will have a free-form speaking and discussion zone. So we could start with the manual part of our presentation, I think.
Sure, let's start or maybe continue. The topic we will cover in this talk is the relaxed structures we need in some scenarios. And first of all, let's take an example on where relaxed data structures can be extremely efficient. And usually we do need them for parallel graph algorithms. And as an example, let's discuss the parallel Dijkstra algorithm. I hope that everybody is familiar with the classic Dijkstra algorithm, but if you don't remember it, we will discuss it right now. So they did the following. You have priority queue. And the graph nodes are organized. So the priority of the node is the distance to this node. And the start vertex, its distance is 0 initially, and you add this start vertex into the queue. And after that, while the queue is non-empty, you extract the node with the lowest distance, thus with the highest priority, and you relax all the outgoing edges. So you recalculate the distance to the outgoing nodes. And if you improve the distance, you insert the corresponding node into the queue. And you do these iterations until the queue becomes empty. So here we have a while loop, right? And if you want to make this algorithm parallel, then the idea is to process these iterations in the loop in parallel. For that, we run this loop in 3 threads, and we replace the priority queue, the sequential version, with the concurrent version. And today we'll talk about how to build this concurrent priority queue. But let's first of all discuss a little bit more the parallel test algorithm. So this algorithm, is it correct? Let's take a look. So we simply replaced priority queue with the concurrent priority queue and run the loop in parallel in 3 threads. No, actually it's not correct, because it's possible that after you add the start node, the first thread, it comes to the queue, it extracts this node, the only node in the queue at the moment. And after that, all other threads detect the queue in the empty state, and thus they finish. So there is no parallelism in this case. But the work will appear later. So these threads should just wait. For that, one of the, maybe not the most efficient, but one of the solutions is to maintain the number of nodes that are in process, and we replace the condition of the loop from queue is non-empty to the number of active nodes in process nodes is greater than 0. So before inserting a node to the queue, we increment this counter, and at the end of the loop, once we are done with the current node, we decrement the count. So in this case, all the threads finish at the proper time. And it seems that we fixed the problem. But is this algorithm correct now? Just think. Try to analyze. Okay, let's analyze together. Let's say we have two iterations that we perform in a parallel, and during each iteration, we extract the first node, the node with the highest priority, and process it, right? And here, it's possible that the first thread, it extracts the node with the highest priority, with the lowest distance. And after that, the second thread extracts the second node. And importantly, it's okay if the second thread relaxes all the outgoing edges before the first thread, right? So it turns out that we have processed the second priority node earlier. And only after that, we process the first node. The first node, right? And it turns out that this algorithm, it's not Dexter anymore, because in Dexter, we have to guarantee that we process all the nodes in the order of the priorities. But now, no, we violate this requirement. So it's possible that the distance we write for the nodes is incorrect. And to fix that, when we process an edge, we try to relax the distance of to the corresponding node, and only if it is relaxed, only the distance is relaxed, we insert the node to the queue. Okay, and now it's correct, so you can implement it. Moreover, if you do the practical tasks I prepared for you, you will find parallel Dexter algorithm there. And if we compare the parallel version of Dexter with the sequential algorithm, then in the sequential algorithm, it's guaranteed that we visit each node exactly once. But in the parallel version, it's possible that due to these inversions, it's possible that the distance to the node is improved multiple times. So thus, it is added to the queue multiple times. It's processed multiple times. And it's okay. And with the parallel version, we obviously win by parallelizing the work. And yes, we lose by performing this additional waste work when we process nodes multiple times. And what is interesting is that in practice, we win much more than we lose with parallelization. And here, probably we can stop for a while and maybe answer questions if you have questions.
Well, we don't have any questions in chat for the moment. If you like to wait, you probably should show the slide where the modified algorithm is shown. Or we will go later, fast.
Yeah, let's then move forward. Okay. And this scheme with as we just used for Dijkstra, we can use it for many parallel iterative algorithms, not only for this, or for many graph algorithms, for Delaunay triangulation. So there are a lot of iterative algorithms. And this priority, concurrent priority queue, is actually this priority scheduler for the tasks in these iterative algorithms. And in Dijkstra, the task is to process the node and to relax the outgoing edges. So what do we want from such a priority scheduler? We want it obviously to be fast, like in any scheduler. We want it to be scalable. And importantly, we don't really need it to be fair. We don't really need this priority queue to be really priority queue. Because even if we replace priority queue with the stack, with the FIFO queue, with the priority queue that returns the element with the lowest priority first, then the algorithm, our Dijkstra algorithm, will be correct anyway. because we do have inversions, we need to cover them somehow. So we should always be able to deal with such inversions. So if it's fine if the solution is not fair, but it should be fair enough. So if we extract an element which is not with the highest priority, but with with high priority, one of the highest, with the top priority, then it's okay, no problem. And if it helps us to construct a really fast and really scalable algorithm, then it's great. And when we talk about priority concurrent queues, then the fastest concurrent priority queue maybe is a queue with is a binary heap with the mutex, or maybe binary heap that leverages the flat combining technique. But anyway, we don't know a really scalable solution. But if we can relax the semantics, then we can build a much better solution. For example, the state-of-the-art priority schedulers in the academia, ABIM and PMOD, they use pretty much the same structure under the hood. They split all the tasks into the baskets, and each basket corresponds to one range of priorities. And in this basket, the tasks are unordered. So it's not a fair solution, right? But it's good enough. It's good enough. And another interesting design, which in my opinion is significantly more interesting, is a multi-queue. So the idea is pretty simple. Let's say we have a lot of priority queues. Usually, if our system has T threads, then the number of priority queues is T multiplied by some constant C. Usually it's 2 or 3 or 4. And we have all these queues. These are sequential priority queues, sequential binary or DRE heaps. And all these queues are protected by locks. And when we want to insert a new task into this schedule, then we choose a random queue, we try to lock it, then we add the task to this queue and release the lock. So after that, insertion is finished. If the queue is already locked, then we try another queue. As we have more queues than the number of threads, then it's likely that we will find an empty queue in short time. Okay, but when we need to extract the task with the highest priority, we choose 2 queues, and between these queues we choose the one which has the task with high priority. So we don't go through all of these queues. We choose only 2 of them. And of course, after that, we choose on these queues, we lock it, we extract the highest priority task from it, and release the lock and finish. And interestingly, this scheme, it provides very good fairness guarantees, and we can see this in practice. We can see this in many theoretical papers. So it's very efficient scheme. And if we compare the classic ABIM and PMOD schedulers and the multi-queue design, then we see the following. So here are the graphs for different benchmarks. So we run different parallel algorithms. One is a breadth of first search. The second one is actually kind of Dijkstra. And the last one is the A-star algorithm, which also finds the shortest path between nodes. And and here you see the speed up over the classic speed up over over the time required for the parallel algorithm to complete with the classic multi-queue scheduler we just discussed on one thread. And here we change the numbers of threads and measure how good the speed up is. And on the bottom, we also measure the work increase. Remember that if we process nodes out of order in Dexter, it can add some waste work. And this metric in the bottom can help us to understand how much waste work we perform. Here we see that with the ability mode, we perform much more work. And with the multi-queue, no work increase at all, right? And we also see that ability mode are much faster because they don't need to do a lot of synchronization. So if there is no work increase in all algorithms, like in the middle, then ABIM and PMOD are significantly better. And sometimes, for example, like on the graph on the right, multi-queue design is much, much better. And on the left, multi-queue is close, but not as good as PMOD. And here's the question. Can we modify the multi-queue design to achieve better results? And before going to the answer, let's discuss the multi-queue, maybe answer some questions. Dmitry?
We don't have questions from our auditory, and I would ask why we should compare a couple of queues. Is it a crucial part of the design of a multi-queue approach or not?
So, yeah, thanks for the question. So here, in the release procedure, we choose two random queues, and we choose the task with the higher priority. If we look only just at a random queue, then the solution will be not so fair. So let me put it this way. Let's say we have a priority queue, and all the tasks have some priorities, and the task with the highest priority has rank 1, the task with the second priority has rank 2, and so on. Okay, that's how we define ranks on the tasks. And with this design, when we choose only two queues, the expected rank depends only on the number of queues. It doesn't depend on the number of tasks you have in all the queues, just on the number of queues. And if you don't do this trick, if you simply go to a random queue and delete the top element from it, then the expected rank depends on the number of elements in all the queues.
Okay.
Clarified?
Okay. And I think But if you have a lot of threads and much more queues, then this algorithm maybe should be poor scale in the end when the many queues will be just empty.
Why should they be empty?
Because we are near the finishing, and random probing will often find the exhausted queue where no data left at all.
Yeah, yes, you're right. But usually, when you need to analyze a huge graph, then yes, you do some. So the queues are empty at start and at the end, but the rest of the time, or practically all the time, then they are non-empty. So there's no problem.
Okay. So let's move forward. We still don't have any questions from our listeners.
Okay. So let's try to make the multi-queue design more practical, to make it work better. And the first optimization that we can apply is task batching optimization. And the idea is the following. We equip each thread with two buffers. The buffer for the elements that the thread inserts into the multi-queue, and the buffer for the retrieved elements. So the idea is the following. When we insert an element, we insert it into the local insertion buffer, and only after this buffer is full, we insert it into the multi-queue in a single batch. So we don't go to the multi-queue every time, but instead we insert elements in a batch. It's more efficient because we don't need to acquire logs each time. We don't need to synchronize between threads and so on. And when we retrieve elements, we delete multiple tasks from the multi-queue, storing them in the retrieval buffer. And after that, we process these tasks one by one by this thread. And we, of course, win by performing much less log acquisitions. We also have less cache misses because most of the time we work with the thread local buffers, and this optimization significantly reduces the contention on the multi-queue. But as we put elements into a buffer, then we put all the elements into one queue, not into several queues. So we also retrieve elements in a batch. Of course, we lose some fairness. Okay, but it's still good optimization. You'll see how it works later. For that, let's discuss another possible optimization. Instead of losing a lot of fairness with the task batching optimization, it's possible for a thread to choose a queue and make it temporarily local for this thread, so that all insertions and deletes are performed in this queue. And thus, we don't need to go to different queues every time, and it should be better, right? So how does it work? So a thread, it chooses a random queue, and it makes it temporarily local, and the following fixed number of operations is performed with this queue. And after that, the thread changes the temporary local queue to another one. It's of course possible that different threads use the same queue as a temporary local one, but it's quite rare situation because we have more queues than threads. So sometimes we are unlucky, but we shouldn't really care about this. And with this design, we we can provide better fairness compared to the task batching optimization because we really update the queue each time. So the tasks we extract are more likely to be the top tasks in the overall schedule. But comparing to the task batching, we need to acquire and release the corresponding log on every operation. And the last optimization that we will discuss is optimization for NUMA systems. So many machines have multiple sockets, multiple CPUs, and it's always expensive to access the same data from different CPUs. For example, here with the multi-queue design, if we access a queue from the first CPU, then from the second one, then from the first, and so on, it's really expensive. It would be much better to access some queues from one CPU and other queues from the second CPU and so on. So it would be better to have a structure like this, when queues are assigned to CPUs. But to guarantee fairness, even if a thread is on the first CPU, it should check the queues assigned to other CPUs from time to time. But we can do this. We can do this with much lower probability. So we work with the queues assigned to the current CPU usually, and sometimes we check other queues. And we of course should never use out of the socket queues as local queues for the temporal locality optimization. Okay, so we of course win by performing less out of socket accesses, but we lose some fairness. So there were different optimizations, and let's see how they work. And here, the MQ optimized and NUMA algorithm is the algorithm with these optimizations. So I should say that for insert, we apply either task batching on temporal locality, and for the it, we apply either task batching or temporal locality. I don't really remember in which case which optimizations were applied. We tuned the algorithm as well as we tuned P1 schedules. And here we see that with these optimizations, the classic multi-queue design becomes much more efficient. For example, on the graph on the left, now this optimized multi-queue is it's much better than a P1, right? So it almost twice faster. On the graph on the right, we have some performance improvement, but multi-queues were better than P1, and now they're even more better. And in the middle, we see that it was a good improvement over the classic multi-queue design, but at P1 are still faster. Okay? Because P1 are faster by design. They don't need to use logs at all. They don't use priority queues under the hood. So the synchronization is significantly faster. But we will try to fix it. Before that, I would like to say that, interestingly, remember with the multi-queue, I mentioned that this design, when you choose two random queues and delete a better task, this design guarantees some fairness. And with all these optimizations, with task batching, with temporal locality, the guarantees are still provided. So for the theoretical part, we do need to add some parameterization depending on the choice probabilities, on the buffer size. The choice probability on replacing the current temporary local queue to another one. So we do need to add some parameterization, but essentially, this optimized solution provides the same fairness guarantees. And if we go back to the previous slide, we see that there is no work increase compared to the classic multi-queue design. But the performance is much, much better. So let's take a pause here. Maybe there are questions now.
Well, we have one question about choosing why we should compare two queues, the same that I was asked before, with some more details, but I think that deep dive should be left for Zoom meeting after, because it requires some probability theory discussing or something like this.
So in short, with the one queue, we don't have any fairness, and with two queues is good enough, and we can, of course, check 3, 4, 5 queues, but it doesn't help a lot. So it will improve the fairness, but with the two queues, it's already good enough. That's the answer.
Okay. So that's all questions for a moment.
So let's try to improve even this algorithm. Let's try to beat a beam and promote. And here we come to a new design, which is called stealing multi-queue. The idea that we want to use these temporary temporal locality and task batching optimizations together. And for that, we equip each thread with a thread local sequential queue. And most of the time, we perform insertions and deletions to this queue. And these queues are not protected by locks. So when a thread accesses the queue, it shouldn't acquire and release the log. It shouldn't do any atomic operation at all. And thus, it's much, much faster. But we do need to guarantee some fairness, right? Thus, with some probability, we go to another queue. Actually, yeah, we go to another queue, and we steal multiple tasks, storing them in the storing tasks buffer. And when we go to another queue to steal, we steal only if the top task of this another queue is better than ours. Otherwise, we don't steal. So it's very close to the multi-queue design, right? So but instead of choosing two random queues, we always choose our queue and a random queue, and decide whether we need the tasks from the random queue or our tasks are better. And if we need them, we steal them. And we do stealing with the constant probability. So the design the following: we have sequential priority queues and thread local buffers for the storing tasks. When we insert a task, we simply go to our thread local sequential priority queue and add the task to this queue. And when we delete task, first of all, probably we previously stole tasks, so we need to process them at first. So we check whether the stolen tasks buffer is non-empty, and if so, we process the first task from the buffer. Otherwise, with some constant p-steal probability, we try to steal tasks from another queue and process the first one. And this try-steal procedure, it also fills the storing tasks buffer. And otherwise, as we decided not to steal, we work with the thread local queue. So we delete the top task from our thread local sequential priority queue. And if it's not found, we try to steal again, because we need to process something. Okay. And here, try steal. It works the following way. We choose a random queue, and we check whether the top element of the random queue is better than the top element from of our thread local queue. And if so, we perform the stealing. Okay, so we steal multiple tasks, and if this steal is not successful, we return null, saying that the stealing has failed. And if the stealing was successful, we return the first element as a result, and all of the tasks we insert into the storing tasks buffer. And now we only need to understand how to implement this add local function, which insert tasks into our sequential priority queue, how to extract the highest priority task. But additionally to these two functions, we also need to check the top task from another thread. And we also need to be able to steal multiple tasks. So we can't use really sequential algorithm under the hood. We do need a tricky data structure under the hood to perform the stealing. And before going to this part, let's answer some questions.
Well, we don't have any questions, and mine was about which queues should be thread safe after all for the solution.
Yeah, that we'll discuss in a minute. But
okay.
Maybe another question?
No, for the moment.
So then I assume that everything is clear. Okay, so we need to organize stealing somehow. And here we'll have a quite tricky implementation. And this, I just need to remind that this mini series is called Introduction to Concurrent Programming. And this particular part will be quite complicated. So if you don't understand it, don't fully understand it, it's totally fine. I will also give a reference to the corresponding paper, because it's hard to understand complex algorithm in 10 minutes. Anyway, I will try to describe it. At least I will describe the basic idea. The basic idea that we will use d-array heaps. So these are like binary heaps, but in the binary heap, on each kind of node, it has two children. And with the d-array heaps, it has d children. It's just more cache friendly. And for the stealing, these diary heaps are also equipped with the special stealing buffers. And threads will steal from these stealing buffers. And for synchronization, we will use epochs and the stolen flag. And this epoch is just a number which increases on every stealing buffer update. And the stolen flag shows whether the elements are already stolen or not. So it helps the threads to synchronize when multiple threads decide to steal from the same queue. Okay. So let's see how add local should work. As for the add local procedure, it simply inserts the task into the diary heap. And after that, if the tasks in the string buffer that are already stored, it fills the buffer. So the idea is that each thread, it maintains the string buffer. So it inserts tasks into the string buffer to make it possible for other threads to steal. And here we check that we need to fill the buffer. And if so, we fill it. We'll discuss how to do that. So just add the task and fill the buffer. In order to extract the top task from the local diary heap, we simply delegate this function to the heap under the hood. So this is not a problem. And to obtain the top element, we do a trick. So the idea that each time we fill the buffer with the elements, we increase the epoch. And reset the stolen flag. Here we read the epoch and the stolen flag, and we store them in a single register, actually, so we can read them atomically. And we read the epoch and the string flag, and if the tasks in the string buffer are already stolen, so the string flag is true, then we return null, because there is no element, right? Otherwise, we read the first element in the string buffer, and this is an unsafe operation because we don't protect the string buffer. Protect it with these tricky epochs and the stolen flag. And after that, we check whether the epoch is still the same. And if the epoch is the same, then we return the top element. So it means that nothing has changed in the meantime, so we can return this element. And otherwise, if the epoch has changed, then we restart. It means that the local that the owner of this string buffer has just updated it. So let's try to read the data again. But if the epoch is still the same, we do guarantee that the string buffer content was the same from the beginning to the epoch check. And when we, so here, yes, this, and when we steal, we do a similar thing. We first read the current epoch and the current status of the string flag, and if we see that everything is already stolen, then we say, oh, there is no element to steal, which on an empty list. And after that, we if there are elements to steal, we did all of them. We did them in unsafe mode, so we are not sure that we collected proper tasks. Maybe the buffer has changed during this unsafe read. But after that, we tried to do the trick. We tried to replace this epoch and stolen flag. No, we tried to set the stolen flag from false to true if the epoch is still the same. So if the epoch is still the same, it means that the content of the string buffer was the same from the beginning to this check. So this unsafe read was actually safe. And by changing the storing flag from false to true, we guarantee that it's us who actually stole the tasks from the string buffer. In this case, we return the tasks, and otherwise, in this class files, we start from the beginning. And to fill the buffer, we clear the string buffer. We filled with the content from the thread local diary heap. After that, we update the epoch and the stolen flag. So we say, okay, this is a new content, so the epoch should be increased. And now these tasks are not stolen yet, so the stolen flag is false. So it's quite tricky, right? And I think, Dmitry, you have some questions, and probably you will help me to clarify the most complicated parts.
Well, I think even I can't comprehend it so fast. So I don't have a special question, but maybe one I would ask, do we extract some part of our task to the steal buffer, or it's just a copy, so we have just redundancy and don't try to modify the queue from which we are stealing?
So we never modify the queue from which we are stealing. We just
so stealing buffer clear is safe because we could just try. If we are not lucky, it's okay.
So let me change the size. So here, in the steal procedure, the only place when we access the string buffer read that simply reads the content, does nothing else, right? And in the top implementation, we did on the first element, but in fill buffer, when we invoke the clear procedure, so it should just work. So it should just clear the buffer. So under the hood, this string buffer is just an array with the counters for the actual end of the buffer. So we simply reset the counter, and here we simply set the counter in the implementation.
Well,
after that, we
extract pop removes the element from our queue.
Yes, of course, it removes the element, because now this element, so we remove it, we put it into the string buffer, and thus we say to other threads, hey guys, you want to steal elements from me? Here they are. you can do that. So it's in this case, the stealing procedure actually steals the elements.
Okay, and only owner thread working with still buffer for writing. So he's also okay.
Right.
Okay.
Only the owner invokes field buffer. So other guys can only invoke top and steal functions.
Mm-hmm. Mm-hmm. So in the worst case, we will just get some tasks from the still buffer and do it, duplicate it with our own.
But we never duplicate it.
Well, maybe we should. But maybe I should better understand the whole scheme.
So in the field buffer procedure, we physically extract the top task from the local diary heap. We add this task to the stealing buffer.
Yeah.
So in this case, we can't extract it from the local diary heap again, right? Because we already extracted it.
Mm-hmm.
So we don't process the same task twice.
Okay. Yes. And our top is attempt to use the still buffer when we.
Yes, and the top implementation, it first reads the epoch in the stolen flag. After that, it checks, actually it should be current stolen. If the flag is true, so there is no element to steal, then we return null, because no elements to steal. And then we read the first element in the buffer. But we are not sure whether there is an element, whether it's safe to read it, because the string buffer can maybe changed even multiple times. We need to check that the content of the string buffer is,
and our
changed.
Operation is maybe performed by any thread or only owner of the queue?
No, this top should be performed by another thread because
but it doesn't extract an element from the buffer.
Yes, it doesn't extract. Exactly, we need it because we. So remember with remember this design. In this design, with some probability, we go to another queue and steal multiple elements. But we do that only if the top element of another queue is better than our top element. So we need to read the top element before stealing. And that's why we need this function. And this top function is called by other threads, not by the owner.
Okay. Well, maybe I didn't just understand all the details, but it would take much time to do it better.
It's really complicated, to understand all the details, but the idea is that we use the diary heap under the hood, and we have a special stealing buffer for the stealings, and we synchronize the content using the epochs and the stolen flag. So this is the idea. So we have a tricky way to do that. Just to trust me, I checked. It works. But yeah, it's not easy to understand this algorithm. I agree. That's why I will also give a link to the paper which describes all the details pretty good. And for the listeners, I would say that it's okay if you don't understand all the details here. You see, even Dmitry, and he's big expert in concurrent programming, and even for him, it's hard to understand all these details in 10 minutes. I wouldn't understand everything in 10 minutes as well, to be honest. So it's totally fine. But one thing that you can learn from these 10 minutes is that if you can avoid creating complex algorithms, avoid it, because it's hard to program, hard to test concurrent algorithms. But sometimes you do need to do that, and now we can check how this design, how good is this design, whether it improves the already improved multi-queue design or not.
Well, we are run out of time, so you should wrap up, I suppose, and then we will move to the discussion zone.
Yeah. So in short, now we are much better than the optimized version of the multi-queue, and we are much better than the classic PMOD and beam schedulers. And yes, let's move the rest to the discussion zone.
Okay. So we are finishing here. It's okay, or you show something?
Sure. Let's finish here. The only thing that I would like to show that if you want to implement the parallel text algorithm, and maybe this, maybe the classic multi-queue design. This is the paper on this string multi-queue. And if you want to implement something related to this talk, you can also check this repository with the task assignments.
Well, so it's all for the official part, and now we will move to the Zoom discussion zone in a couple of minutes. Join us if you want to ask some questions. At least I am frightened enough by the last algorithm. And we will talk there. And don't forget to rate our presentations. Thank you, everyone.